an enhancement to the Breault GTX file format, allowing interoperability between the SolidWorks Parts 3D modeling engine and ASAP 2008, now allows users to assign layers and object names within SolidWorks prior to analysis in ASAP. Within SolidWorks, users may select any objects they wish to group in an optical property layer. Right-click on them and place them in a GTX layer with a specified name. After this process is completed, the SolidWorks file may be saved in the GTX format and opened in ASAP 2008. Within ASAP 2008, users will notice all naming and layering assigned in SolidWorks is retained. This includes both layer names and object names. These layer and object names will be present throughout any visualization and analysis performed in ASAP 2008. We are excited to announce that the ASAP 2008 release includes numerous polarization ray tracing enhancements that open up new possibilities for device design and analysis. A key demonstration of polarization analysis is the appearance of a so-called Maltese cross pattern in the throughput of a cross-polarizer pair. ASAP 2008 is able to show such a result using the new realistic polarizer model. A distorted form of the Maltese cross pattern can be produced when cross-cylindrical lenses with skewed conformal polarizers are analyzed. Another new polarization device type, the Jones element, can be used to simulate a polarization retarder. For instance, the effect of a conformal quarter-wave Jones retarder on a linearly polarized input may be assessed. Such a quarter-wave retarder can also be examined using rays with their polarization states randomly perturbed, a new source randomization feature. Simulations may include individual polarization devices that are cascaded. For instance, a one-way isolator model is a cascaded realistic polarizer and a Jones quarter-wave retarder. With off-axis illumination and a skewed device orientation, a skewed Maltese cross results. Polarization of sources may be randomized. Ellipticity and orientation may be randomized individually or together. Enhancements to the list rays command allow users to output polarization data for individual rays. Views include polarization data in Stokes vector form and also in Jones vector form. Another enhancement allows polarization information to be saved with ray set data using the dump command and then reloaded using the emitting data command. Two sources with a slight lateral offset between them can be created using this technique, resulting in a smeared Maltese cross. The same technique with a narrower beam results in separated Maltese cross patterns for the two sources. This approach can also be used for simulating an axial displacement of the two sources, as may occur when there is a ghost reflection. A slight axial twist shows a shift of energy among the peaks, with the shift of one source opposed to the other. Finally, the Poincare sphere visualization tool in the 3D viewer enables graphical examination of polarization states. Each polarized ray is identified by its polarization state, wavelength, and flux. Location on the sphere shows the polarization state. Wavelength is given by the marker shape, and flux may be shown by the color. The flux mapping can even be done in either a linear or logarithmic way, and limits may be set to see fine variations. By pointing to a ray data marker, a detailed set of numerical data are shown in a pop-up box, including index number in the dump file, flux, wavelength, position, direction, and polarization state. These data can also be sent to the output window. Together, these enhancements represent the next level in polarization ray tracing capabilities available to optical engineers and designers. The ASAP 2008 release includes a rich set of optimization tools with a wide range of applications. 3 new optimization methods are included in the ASAP 2008 release: a Brent's method routine for single variable problems, as well as downhill simplex and simulated annealing methods for multi-variable problems. From the scripting interface, users may enter into an optimization environment where they can define design variables, set minimum and maximum values, and, if desired, step sizes and manufacturing tolerances associated with design variables, define design objectives and set target values with weighting factors, define design constraints and set exit criteria, and select the most appropriate optimization method. While running an optimization, ASAP 2008 will display numerical and graphical information about all of the trial solutions. Even trial solutions that depart from the ideal solution will be displayed, demonstrating thorough exploration of solution space. Upon completion of the optimization iterations, optimization data is automatically saved and can be further analyzed to evaluate solution space. These optimization methods, now available in ASAP 2008, represent a leap in the design power available to optical engineers and designers. Also in ASAP 2008 is a redesigned HTML help system, benefiting both new and experienced users. Help sections described on the welcome screen include features in ASAP, the ASAP interface, building your system, a step-by-step guide, a quick reference guide, commands and macros, and scripting language concepts. Users can now expect improved help topics, easier access to parent topics and related information, and point-and-click access to example scripts. From the scripting command line, users will notice automated command tips with linkage to command references and example scripts, with the option to cut and paste directly from example scripts found in the HTML help system. This concludes our overview of enhancements available in the ASAP 2008 release. Please visit the Breault Multimedia Gallery at breault.com for full-length demonstrations of these new features by Breault engineers. And turn your creative ideas into working prototypes with ASAP 2008, the world's most sophisticated, industry-standard optical software, offering optical engineers and designers unmatched capability, flexibility, speed, and accuracy.